I'm Lucie Green and I'm a space scientist working at University College London's Mullard Space Science Laboratory. The Mullard Space Science Laboratory is the UK's largest university-based space lab, and in this building we have around 180 people who are doing not only scientific research looking at things like black holes or galaxies, star formation or the sun, which is my specialist area. We're also building the instruments that we need to be able to do this research. Everything happens on this site. My new book is called 15 Million Degrees, and that's in reference to the temperature at the centre of our local star, the sun. And really in the book what I wanted to do was convey just how far we've come in understanding our sun, but also the work that it's taken to get there. So I wanted people to get a sense of what the real sun is like. So to move away from seeing the sun as perhaps a placid disk in the sky that we completely take for granted, and transform people's views so that they see it as this violent and dynamic object that it actually is. I first got interested in space science as an older teenager, and I think it really grew out of a love for physics. I always liked using the framework of physics to answer questions about the world. And I do remember distinctly one time that my parents said to me, "Oh, what about thinking about astrophysics as a subject to study?" And I remember thinking, "Oh, I don't know what astrophysics is. What is this strange word? What does it mean?" And so I went away and I started reading magazines like Astronomy Now, which talk about astronomy and astrophysics. And that was when I realised, of course, you could use the whole universe as a scientific laboratory. And that's when I got interested in astrophysics, and then from that into the sun. So if we come round here, these are our mechanical workshops, and this is where we build instruments that go to visit the sun, Mars, Venus and more. So come in and have a look. Here we have the bits of kit that allow us to take our designs of different instruments that we want to send into space, and we can start to cut them up, cut into the metal, have the instruments take shape and start to do the build of the instruments here as well. We're very keen to explore everywhere in the solar system, but for me the sun is the centrally most important object. And what we really want to do in the future is get up close to the sun and be able to see it from close proximity, and also measure the emissions that come from the sun, so emissions like electrically charged particles and also magnetic fields that get dragged away from the sun. And so the mission that we're working on at the moment is called Solar Orbiter, and this is a model of one of the instruments that we're building. So we're involved in two aspects. One is a camera that's going to look at the sun in extreme ultraviolet light, so a wavelength that our eyes can't see, but which the sun shines very well in. And then this is an instrument which will sit in those solar emissions and measure the particles directly. And this one in particular is going to be measuring electrons, so negatively charged particles. So this is one of the models in a sequence of models that we make, so that we make sure we've tested them, that they're robust and that they're going to survive in the extreme space environment. So this place is full of surprises, and I'm going to take you to another quirky aspect of this department, which is a facility that we built to contact our satellites and our instruments. And here we have it. This is our station to contact the instruments that we have on some of the satellites we work with. Looking for radio signals from other advanced civilizations is something that is actually happening in research. And my personal view is that it's a long shot, but we should be doing it. And actually this antenna here, it illustrates really why we think that way. So this is a facility that we can use to send and receive signals from spacecraft, so we can communicate with them. But the bigger picture is that because we use radio waves to contact spacecraft, we use radio waves also to broadcast radio stations and TV stations. All the time we're sending this information out into the universe, or at least into the galaxy. So the idea is that if we're doing that, other civilizations might be able to pick up our radio signals that propagate away from the Earth, and perhaps vice versa, we could pick up radio signals that they're sending out, either on purpose or accidentally as we are. But it's a big sky out there. So it's like finding a needle in a haystack if indeed life does exist anywhere else in our galaxy. But it's a tantalising thought that one day the signals we send out might be picked up, and that one day we might find evidence of advanced civilizations through their radio signals. When it comes to the male-female ratio in science, I think it varies by area. So for my area in astrophysics, my personal experience, and I think from looking at the numbers, is that we're not doing too badly. I think at the senior levels there's an underrepresentation of women, so if you're looking at female professors, but actually in my group, in my department, we're pretty good. So we have 3 female professors in the solar group. In fact, all our staff members are female in the solar group, so we're dominating here. But then when you look at younger areas, the trend is that you have more representation of women as you go to lower or younger ages. So my hope is that as they progress through their careers, the gender balance will improve in the years to come. But it's still an issue that needs talking about, and it's still an issue that needs awareness. We don't have gender equality in terms of numbers in my area or in physics in general, but there is a concerted effort to raise awareness of that issue and encourage girls who are interested in doing physics to do so. The big questions that I'm interested in are to do with the sun's dynamic side, and in particular related to a phenomenon called a coronal mass ejection. So it's not a phrase that rolls off the tongue, and it's not a phrase I think that's particularly well known, but these events are huge eruptions that take place from the sun's atmosphere, blasting the same mass as a mountain into the solar system at speeds of maybe up to 2,000 kilometers a second. So personally, I'm interested in where does the energy come from to power these events? What are the physical processes that trigger them and drive them? And this means that I'm very interested in studying magnetic fields, because actually we think they're magnetically driven. But there's lots of questions about the sun that we want to answer.